Hello and welcome back to our reading of categories and sheaves. Today we're going to be continuing our reading of categories and sheaves with section 1.4, which deals with the Yoneda lemma. And this lemma is arguably the cornerstone of the chapter. It's easily the most general result that we've seen so far and arguably the most profound. And we make no attempts to say everything that one can say about this important lemma in this video. In an attempt to say some of the things that we can say about the Yoneda lemma and its broad applicability, this video will be followed up by at least one, maybe two more, dealing with applications of the Yoneda lemma, some of which we'll show or talk about in this video just to sort of whet your appetite for the subject, but then at least one more on some details of at least one place where the Yoneda lemma is realized in a concrete situation, maybe not a concrete category, but in a concrete situation where it will actually be extremely useful to in that setting. So the main thing that we need to talk about the Yoneda lemma is to introduce the notion of a pre-sheaf or of a co-presheaf. And before we sort of get started with that, with the most general definition, we'll give a sort of concrete definition, which comes from topology, because this is the setting in which it was originally conceived and the setting in which you should have in mind while you're thinking about pre-sheaves or co-presheaves, at least for now. So to do that, we let X be a topological space, and a presheaf is something we're going to put on to X. So we take the topology on X, and we give it this give this the structure of a category in the following way. We declare the objects of this category. What should I call this category? Maybe I'll call this T, because a topological space is typically denoted by xt. So the objects of T will just be the elements of T. In other words, the open sets. And hom uv will be either the inclusion map, if it exists, that is to say, if U is actually a subset of V, or the empty set otherwise. And this definition is basically just turning the topology on X into a poset. And we've seen examples of categories of posets. So this is nothing unfamiliar into a poset this way. Okay, and then what we can do is make a definition of a presheaf out of this, where we simply take our definition to be that of a contravariant functor from this category to a given category. So let's get that precise. A presheaf, and we always speak of a presheaf having something, right? So I'm going to make the definition for presheaves of sets, but you could make any kind of presheaf you want by just changing sets to be some other category. But a presheaf of sets on X will be nothing but a contravariant functor from this category, which I've called T above, to set. And so basically all that means, and I should give this a name, we usually use script letters, or at least I usually use script letters because I grew up reading Hartshorne, who uses script letters. So I'll use script letters. And so all this means is for every open set, we associate some set. And whenever we have an inclusion U inside of V, the contravariance gives us a restriction map FV to FU, which is usually denoted by either some F's or some rows. Maybe I'll use little f's to sort of keep with the theme. And we use upper and lower indices to say which is which. And we call these guys restriction maps. Okay, so this is our definition for of a presheaf. And like I said, we can make definitions that are sort of increasingly general by replacing set with some other category. But with this sort of intuition in mind, once one has had some experience with pre-sheaves, one knows, and we're going to see this as we read, well, categories and sheaves, that there's really nothing about this that requires the topological space, or even the post-set category. So what we do is we upgrade this definition to a category theoretic definition that doesn't make any reference to any specific category. So what we're going to do is define essentially a pre-sheaf on a category. Actually, I hesitate to say that because maybe we'll mean something else by that in a little bit. But anyway, I digress. So we take our small category. We're recalling that U means U small for some universe. And then we consider the category of functors. And remember, we borrowed this notation from set theory. Set C op. And also we have set op. C op. And the former category we're going to call the category of presheaves. Well, to be specific, it's the category of presheaves of sets on C, and we denote this by PSH, and we'll call this, I just have to decide my notation once and for all. Let's put the presheaf of sets on C. We'll put it in this order, just because that's the order in which I say it. And then the latter category will just be co-presheaves of sets on C. Now, a couple of remarks. The first is that this category is not going to be U small for any reasonable category. I mean, I haven't thought too hard about the set theory stuff. Maybe if it's like finite sets or so, it's fine. Or a finite category, it's fine. But in general, this category is just going to be really, really huge. And the reason is just because, actually, I think never. Because sets have a proper class worth of sets. There's no biggest set. And so just in general, when I take whatever this is, well, your intuition from set theory and from cardinal arithmetic should sort of inform you that this thing is just going to be much bigger than whatever I started with. When we bump into things like this, we call these categories large rather than small, remembering that this sort of has this relative meaning to some universe. But the point is that no matter what the universe is, when I do this construction, I'm always going to be guaranteed to be leaving that universe. Another remark, and maybe a more important remark rather than a technical remark, is a remark / question, is why co-presheaves? Right? So if I look back at the definition here, there's this weird thing where I have this op and this other op, and that's really strange. Unraveling the definition, just having yourself a brief think, you come to the conclusion that a co-presheaf on a category C is just an ordinary covariant functor to the category, in this case, of sets. So why? Well, the answer is twofold. The first is because I told you so. But a better answer is I'm going to define for you now some functors, which will be the key objects of study in the Yoneda Lemma, which will crucially depend on us thinking about co-presheaves as actually co-presheaves. Of course, it's completely equivalent to think of them as covariant functors, but it's sort of advantageous for phrasing the theorem in a way that respects our principle of duality, to leave things as co-presheaves. Okay, so now that I've made these definitions, I'm ready to define the most important functors. Oh, I should write down the answer. The answer to the question is the principle of duality. Makes it easy to formulate the Yoneda Lemma. Sorry about that. Okay, so now let's make our last slew of definitions for the moment. And what we do is define functors HC from C to PSH set C. And here it's important that this be set, at least to my current knowledge. And what we do is we send X into HOM into X. And we define KC, which will take C into co-presheaves. And it does this by looking at HOMs out of X into the target object. And so this is sort of what's going on and why we like these notions of co-presheaves in terms of as covariant functors, because this is sort of the natural way to think about these HOM functors. Like HOM is not just any old ordinary covariant functor. It has all these familiar properties from algebra, and sort of phrasing things in this natural way makes this more efficient. So with these in mind, we can state our Yoneda lemma, which I would be remiss if I didn't call it a lemma, but really it's a theorem. It's sort of taken on a life of its own. And it says the following. I just put 2 colons. So let's say we have a presheaf A on a category C. And then let's take some object X in C. Then HOM in the category of presheaves, and I apologize for this notation, which looks a little cumbersome, between HC of X and A is naturally isomorphic to A of X. Now remember, A is a functor, right, because it's a presheaf. So what I'm doing here is I'm claiming that this isomorphism is as functors. Well, I guess that's not what I mean, right? Because what I'm doing is evaluating this on the object. So I guess I mean this in C. In set. Wow, I'm really not doing good today. Why? Because A is a presheaf of sets, and we fed in the object. So now it's an isomorphism in set. Whew. And let's get the dual statement right. If we have B a co-presheaf, then the isomorphism is HOM in co-presheaves set C from B to KCX is isomorphic to B of X. Okay, so how do we go about proving this lemma? Well, it's actually not a tremendously difficult proof. There's a little bit of machinery involved, not in the form of any heavy lemmas, but just a handful of layers to the construction. But first, let's start by observing that since the opposite category of a functor category is just another functor category, in particular, it's the category of functors between the opposite categories. That's a mouthful. Maybe I'll just write on the isomorphism. We have F mapping to apply the opposite, followed by F, followed by apply the opposite. And that this is an isomorphism implies it's enough to only prove this for presheaves. So we'll limit ourselves to presheaves to sort of control the level of notation and ops that we have to consider. So first what we do is we construct a map in one direction, and then we're going to construct the inverse. So we have our map from HOM, PSH, set C, HCXA, and I'm running out of room, so let me just scroll over a little bit to A of x. I'm going to try not to do that too much. And we're going to do this in a couple of stages because, like I said, there's sort of some layers to this construction. So first, since HC of x and A are presheaves, they can be evaluated at x. In other words, I can just feed in x. And this sort of replaces our Hom set of presheaves with a Hom set at the level of objects in C itself. And we can take the resulting set of all such maps and get us a map in Hom set. So writing this down, we obtain a map in set Hom C XX AX. And this is sort of follows from our definition of HC. Oh, extra paren. Now, we have a special map, x to x, right? In fact, there's only, in full generality, there's only one map, x to x, that we know is always there, and that's the identity map, x to x. So if I take the identity map, x to x, then I can look at all the maps from id x to a of x. And that's simply a of x, just from the definition. So if I take all maps, then that is simply a of x. And we take the composition of these maps to be our map phi. Okay, so now in order to prove that this is an isomorphism, we have to construct an inverse. So what we do is we associate to each S in AX, we take, we need one piece of data, and Y in C, we take a map, I should be careful, we take a map, which we'll call psi, and we'll index it with some notation to remember where we took it from, and psi of S, I should use the same notation, get it right, psi of SY will be our map Hom, will be a map Hom YX to AY. And so the domain of this is HC of X just evaluated at Y. Right, that's just how we define HC of X. So if we give such a map, then we can put them all together to obtain a morphism of presheaves. And then once we have this, we can put these together and obtain a map that and what does this map do? Well, this map goes then from A of X, because this is a presheaf, into Hom PSH set C HC of X A. And so if we could actually do such a thing, then we would have everything we need. So this is sort of our strategy. Now I have to tell you how to actually construct such a map given S and Y. So suppose we have S and Y as above. Then what we do is we will map now Hom C Y X. I need to put this on a new line, otherwise I'm never going to fit it. Into Hom set ax, ay by simply applying a. Nothing really difficult here. But now the catch is that since S is a singleton, then picking out S actually gives us A of Y. Since S is a singleton. Okay, and if one is really careful about this, one can actually just sort of, maybe that's not the right way to say it. If you just sort of think carefully through our construction, you'll see that these are sort of mutually inverse to one another, and essentially from the definition, right? Because at every step, all we did was just take the canonical things, right? We only took those things which we were sort of guaranteed to have existing to us, and as a result, they're sort of forced to be mutually inverse to one another. To actually calculate is a little tedious, and we've sort of already been here 20 minutes, so I don't want to do this now. Maybe I can do this in the next video if anyone wants to see it, maybe on the Discord, or if there are comments, which I would be incredibly surprised by, but I'm happy to do it if there's some demand. But for now, let's leave this because I want to get to the corollaries and start to say some things about why the Yoneda lemma is important. So there are quite a handful of corollaries that are very important. The first one, and probably the one we'll use the most often, is H and K are fully faithful. And because the Yoneda functors are fully faithful, what this is telling us is that any small category is embedded in a category of presheaves, or co-presheaves, depending, of sets. And a way to think about this is sort of the following rough heuristic. What you do is you think of the category of presheaves or co-presheaves on a category as objects that are more general than the objects of the category, but built out of them, or maybe if you like, modeled on them. And then what we're doing here is that the morphism, and how do I say this? This is sort of true in an abstract sense because the morphisms of the category are the building blocks of the morphisms of presheaves. And then these more general objects, instead of being objects that you can just have, they're sort of objects that you probe by feeding in test objects in C as either targets or sources. And in order for this sort of interpretation to make sense, it has to be the case that given any object, it sort of has to be the same TM to regard X as an object or as one of these abstract generalized objects. And this is what the Yoneda lemma says. And our fully faithfulness tells us that we have this embedding, which sends the original category into a subcategory of these presheaves, which consists of only the generalized objects. So let's sort of see how this manifests itself. It comes up in a handful of different places. And I'll show you at least, maybe I'll show you 2.5 examples. So example 1, the most basic example, and now if you're new to category theory, you'll finally understand the memes. Let's let G be a group. And we know that every group G can be regarded as a category with one object, which we think of as just like a sort of point. And then there are morphisms in G corresponding to the elements of G and composing according to the group multiplication. So like, G circ H would be literally HG in the group. Okay, so now what is a functor from G to set? Well, this is nothing but a choice of a set, because there's only one element, and a map from the group into the bijections of S, because every morphism in G, being a group element, has an inverse, and the invertible morphisms in sets are the bijections. So then a functor G to set is just a choice of a set, and it's, maybe I'll call that set, I don't know, S. And then we, what did I say? We're sending the morphisms onto the some bijections of S. Okay, and so then what is a natural transformation of these things? Well, a natural transformation is a homomorphism of functors. So what that means is it has to be a map between these images in sets so that you would get a natural commutative diagram that relates these different bijections that you would have. So in other words, we would have a natural identification of a group with a collection of bijections on some set. So I want to write that down because it's important. Natural identification of a group with bijections on some set. Now, I don't know if you guys are getting any familiar vibes, but we know a theorem like this, right? We know that every group fits inside some permutation group on some set. Now, I've abused the letter S here because the symmetric group's notation is already S. But if I went back and changed these S's up here to X's, then you would see it. And this is Cayley's theorem. And in fact, I could even just take the bijections to just be, or I should take the set just to be a set of the same cardinality as the group itself. And then the bijections are nothing more than the group table. Of course, you don't have to do this, but in that setting, that's sort of what they are. And if I take some bigger set, well, then it doesn't really matter because the bijections will still compose according to the group law because we have this functoriality. And so whether or not it's literally the group table or just behaving the same as the group table is maybe a question for someone with more knowledge of this than me. To me, this sounds like this is exactly Cayley's theorem. Okay, let's do another example. And for this example, we'll think about posets. And we already talked about how to regard a poset as a category, where the objects are just the elements of the poset, and the morphisms are really given by the inequalities. Now, what does the Yoneda lemma tell us in this case? Well, the Yoneda embedding is telling us that the objects of a category are determined by the hams either into or out of the object, depending on which one we pick. Let's just say out of the object for this moment. Well, what that means is then an element of a poset is determined by all the things it's smaller than. So in other words, an element is determined by its inequalities. And maybe the half example that I don't want to talk about this too much because the construction of R is sort of beyond the scope of this video. But again, if there's some interest in it, I'll show it maybe later on. You can actually upgrade this to work with posets that even contain maybe a little more data than just set theoretic data. You can actually upgrade this machinery to construct the set of real numbers. And it's not completely trivial because while R is a poset, it has more data than just its posetness, right? R is the unique, complete, totally ordered field. And so there's this extra structure here. In particular, it's the completeness that's really interesting here that makes this not a completely trivial application of what we've learned so far. And there's a sense in which what we've done here is actually really quite generic. We haven't seen a tremendous number of categories, and we haven't learned about enrichments of categories yet. But once we have some more of that under our belt, it'll be possible to sort of spruce up these examples to include quite a handful of familiar categories. Okay, let's see another couple of corollaries. There are two more that I want to talk about. And corollary 2 says the following. So suppose we have a functor c to d, and where c is small and d is locally small. Then, if I have a presheaf A, let me not get ahead of myself. So A, a presheaf of sets on D, then we can consider the category C lower A, which we talked about in a previous video. I'm going to try to make a little card come up to link you guys to that in case you need to be reminded. The short version is that this is associated with our map C to D to presheaves of sets on D. And then this category is small. And similarly, if B is a co-presheaf, then C upper B is small. Okay, so how does this work? This is a very easy proof, and you just use Yoneda. So Yoneda tells us that if we take an X in C, then we can look at the family of morphisms given by HC composing with f of x to A, and this is just A of f of x. Nothing really going on here. But what that means is C of A can be regarded as a category of pairs, where the pairs consist of the data x and s, x an object of C, and s in here. But now C is small, so we can just take the disjoint union of all of the A of f of x's and obtain a set. And that's still a set. And the dual case is exactly the same. All right, one last corollary. I think I'm actually going to take more than one more video on this because I didn't even get to representable functors yet, which is arguably even more important. So far, all I've done is tell you the proof of this one lemma. So, okay, for the third corollary, corollary 3, let's C be a category, and f x to y a morphism in C. And what we do then is assume for each w in C, the induced map on Hom sets is an isomorphism. Then in this situation, f is an isomorphism. And we sort of bumped into these ideas when we were talking about monos and epis, but we had some concerns about what would happen with isomorphisms. And now this corollary tells us what happens, but we need the Yoneda lemma. So let's say how this works. The hypothesis tells us that I can look at HC of f, and this gives me something HC of x to HC of y. And, or of course, in the covariant case, I could just use k, but I'm not going to worry about that. Then these are isomorphisms by the assumption, because they have, of course, set inverses. But of course, these guys, when I compose a thing and its set inverse, I get the identity. And since the Yoneda functors are full and faithful, well, maybe you guys even know how to finish the proof. These inverses have to have lifts. Well, I guess that's since they're full, they have lifts. And since they're faithful, they lift to the desired inverses. Lift, maybe I'll say lift uniquely. And that completes our proof. Okay, so I think this is a good place to stop. We're already 35 minutes long. And next time, I'll take note of the agenda for next time, or for the next few videos. Representable functors. That's the biggest thing. And that'll probably be a pretty short video. Too long to tack onto here, but not that long. And then I want to talk about the Brown representability theorem. I promised you guys when I started making these videos that I would show you sort of why one should be interested in all of this category theory stuff. And so for me, coming from geometry and topology, that means places where these results actually appear in non-trivial ways. And what the Brown representability theorem does is it tells us that certain functors in algebraic topology are representable. And as we're going to see in the next video, the representable functors are in a sense the ones that you can get your hands on and calculate with in a very explicit way. And so the Brown representability theorem will establish for us that certain functors in algebraic topology can be understood out of very simple building blocks of topology. And I don't want to say too much because A, I don't want to spoil it for those of you who don't know this cool story, and B, I don't want to drag this on any longer. But I want to at least sketch the proof of this theorem as well as set up some of the machinery of algebraic topology for you guys. And then maybe, this is a big question mark, I want to talk about the functor of points in algebraic geometry. That one's a little harder because, I don't know, like I don't plan on doing the Brown representability theorem in full detail because I can sort of wave my hands at places, like when I'm setting up what some of this stuff does. You don't have to understand everything to understand what the theorem is saying and to get something out of it. But algebraic geometry doesn't necessarily have as many niceties. Like I'll have to say what a scheme is and what an ordinary sheaf is in order to say what a scheme is. And I don't know, that seems like it's kind of hard. So I'll try. Or if people want to see it, then I'll do it. But we'll sort of play that one by ear. And then all that's left is to talk about adjunctions, which I guess I'll call 4. And that'll be smooth sailing. So congrats, guys. If you made it this far, then we're halfway done with this chapter. All right. Thanks for watching. Hopefully I'll see you guys soon.